Okay, so we will get started. We're going to start by looking at surface integrals. So again, as with line integrals, you can have the surface integral of a scalar function or of a vector field. So surface integrals of vector fields called a flux integral. And notice that in either case, right, we have to parameterize our surface, right? Okay. And so that is what G is, so parameterization of the surface, and is any vector that is normal to the surface. And what does it mean to be normal to the surface?
I was going to say, what does it mean to be normal? What question?
In mathematics, no such thing as loaded questions.
Normal to the surface is, like, isn't it like tangent? No.
Not tangent.
No. Hold on, it's in here somewhere.
It's essentially the opposite of tangent.
Perpendicular?
Yes, perpendicular. And so that's the beautiful thing about mathematics.
Yeah, tangent.
Normal actually has a meaning.
Yeah,
It's objective, not subjective. Well, normal is 90 degree, tangent is, it kind of just touches, so it'd be kind of parallel at that point.
Oh,
Perpendicular forms 90 degree.
Right.
So this would be normal, and then you have your tangent, which is.
Yeah. I remember normal from mech, intro mech. Is where I mainly use that.
Oh, good.
Dynamics.
Alright, so I'm going to highlight these real quick. Because this is how we evaluate them, and these are a pain in the ass. Yes, unfortunately.
True words never spoken.
And that's how we're going to evaluate it. Right? It's a double integral over a domain. You evaluate your function along the surface, multiply it by the norm of your normal vector dA. And keep in mind, orientation of a surface is a thing. Normal vector is either going to be the partial of G with respect to U cross partial G with respect to V, or the other way around, depending on the orientation. Unfortunately, unfortunately, you don't know which one it is until you calculate it.
So you're talking about which order they get there.
Right, because you generally will have outward pointing orientation or inward pointing orientation. Right. You don't know which order of the cross product you want until you actually calculate it.
Isn't that right hand rule? No?
Right, cross product gives you the right hand rule, but
yeah.
G is going to be a function. You don't know what the directions of those vectors are. Right.
I see. Okay.
So generally what we do is we'll just stick with this order,
yeah,
and then examine it. Actually, it doesn't matter for here because you're taking the norm of it. Right, but for flux it is going to matter.
So what you're saying is it could be G of V cross.
Yes. But what you do, so just calculate this, and then you look at it and you go, okay, is that pointing in the right direction of the orientation? If it's not, you just flip it. Multiply by -1.
So yeah, it's fine.
So you just calculate one order and then examine it. Right? That's not going to matter for here, but for flux integrals it will. Because now you're doing dot product versus just the norm, right? The norm, it doesn't matter which direction it's pointing, it's going to give you the exact same norm.
Yeah.
But for here, it does matter.
Okay. So is this same thing where you calculate it in the formula?
Just find the normal vector anyway first, and then determine is that the right direction.
For determining if it's the right direction, what would be?
We'll see.
Okay.
It all depends on the surface and what you get from the normal vector. So calculate. Evaluate the surface integral, so the integral of z across the surface of the cylinder, y squared plus z squared equals 4, for z greater than or equal to 0, and x between 1 and 4. So y squared plus z squared equals 4 is the bright circular cylinder, right, that goes along the x-axis, right? So it's coming out at you. And we're looking at only the surface from 1 to 4, and actually only the upper surface, right? Because z has to be non-negative. So we need to parameterize that first. That's always the first step. I'm not going to go through the derivation. Right, read through the book and look through the posted video. We can parameterize the surface in terms of x and y because our surface can be written in the form of z equals little g of x comma y. Right, you can write z as a function of x and y. In this case, z would be the square root of 4 minus y squared. Because z has to be non-negative. If that's the case, then the parameterization is simple. It's just x, y, little g of x, y. Now we need a domain. But they already told us what x has to be, right? 1 to 4. But y? Well, y would go, what, -2 to +2 for that cylinder, right? We now need the norm of the normal vector. And again, it was derived already, so I'm not going to re-go through it. For a parameterization of this form, where z is a function of x and y, it's the square root of 1 plus the partial of little g with respect to x squared. So what's the partial of square root 4 minus y squared with respect to x?
It's just zero.
Yep, it's just 0. Plus now the partial of little g with respect to y squared.
That would still be.
So you want the partial square root of 4 minus y squared with respect to y.
Is it 4 minus 2?
Negative y over the square root of 4 minus y squared. And we square that. Simplify this. It's going to be the square root of 4 over the square root, not square root, sorry, over 4 minus y squared, right? Which is just simply 2 over the square root of 4 minus y squared. So it's the double integral over the domain, over the region D, of the integrand evaluated along the surface. Well, the integrand is just z, right? So evaluate that along the surface. Z becomes the square root of 4 minus y squared. Yes. Times the norm of our normal vector, dA. Right, so ds becomes the norm of our normal vector, dA. Oh, but isn't that going to be just 2 times this double integral? What's a double integral represent? That's just the area of our region. Our region's a rectangle. Four minus 1 is 3, 2 minus negative 2 is 4. 3 times 4 is 12, times 2 is 24. There's your surface integral. And so again, the hardest part is parameterizing your surface. Once you've done that, it's now just a double integral. We're integrating x squared over the surface of the unit sphere. Parameterization of the unit sphere. X, Y, Z in spherical coordinates, right? Rho, cosine theta sine phi, rho, sine theta sine phi, and then rho, cosine phi. But for the unit sphere, rho is the radius of the sphere, right? So it's just 1. There's no restriction, so theta and phi is everything. 0 to 2 pi and 0 to pi respectively. Norm of normal vector. For a sphere, it's the radius of the sphere squared times sine of phi. Well, radius is 1, so it's 1 squared sine of phi. There's the norm of the normal vector. This is the double integral over d, x squared evaluated along G. ds becomes sine of phi dA. Well, now we get to evaluate that integral. Let's do it by hand. Notice, well, actually, I can just write it this way, and I'm going to. It's a product of a function only of theta and a function only of phi, right? So we can write it that way. So let's just examine the integrals one at a time. We can write cosine squared as a half 1 plus cosine 2 theta, right? What is the period for cosine of 2 theta?
It's just 0.
Then it's just pi, right? Well, aren't we integrating cosine of 2 theta over 2 full periods?
So then it's just 2.
I guess 0.
Oh, because 1 period would be 0.
Any multiple of a period, if you integrate a periodic function over any multiple of its period, it's automatic to 0. That becomes pi. Now we have to evaluate that. Do you remember how you did it? Right, the sine squared times sine. Right? Sine squared is 1 minus cosine squared. Now it's u sub. Let u be cosine. Then du is sine, right? Or negative sine, rather. So we're going to multiply by a negative. Integral of 1, oops, sorry, it's not fake. Integral of 1 would just be u, but u was cosine. plus 1/3 cosine cubed of phi. Is it plus? No. It's minus.
Where did you do the research? Oh, it's-
Right, so this just becomes 1 minus u squared du, right? U minus 1/3 u cubed. What is cosine of pi?
Oh, no, it's-
-1.
hmm.
Minus cosine of 0 is 1. -1 minus 1 is -2. Cosine of pi was -1. -1 cubed is -1. Minus cosine of 0 cubed. So that's minus 1 cubed, right? -1 minus 1 is -2. Times that by -1/3. -4/3, and for the sake of space, that's 4/3. Means that's 4 pi over 3. And here we want to integrate z squared over the surface of the upper hemisphere of radius a. So we're just going to parameterize the sphere and restrict its domain. Right? Upper hemisphere means theta is 0 to 2 pi, but phi will go 0 to pi over 2. Right, and then norm of the normal, a squared sine phi. Z squared along the surface is a squared cosine squared phi. The S is a squared sine of phi dA. A is a constant, a squared times a squared, a to the fourth, factor it out. This is what we're left with. Oh, but there's no theta. So if we're integrate with respect to theta, we're just getting 2 pi. This is now what we're left with. This is a simple u sub cosine of pi of 2 is 0, cosine of 0 is 1, 0 minus 1 is negative 1. Two-thirds pi a to the 4th is the surface integral. Evaluate yz, integral yz across surface of the portion of the sphere of radius 2 that lies above the cone, square root of x squared plus y squared. But also going to do that for the left. I wonder, can I do this instead? No, it won't let me do that. Let's do it this way. That's the style. Ah, perfect. But what did I do? Right here, got this. Did that wrong, that should have been 0, 0, 0. Okay. There we go. And again, I always do this. That's good. That's right. Do it this way. So this is the surface. This part here. Right? Because that is the surface of the sphere. It's the part of the sphere that's above the cone. So it's going to be, you can vaguely see like that outline there. That's going to be the cutoff of the sphere, and that's that part. So that's actually called a polar cap. Right? It's part. It's not a hemisphere. It's not a full hemisphere. It's part of a hemisphere. So that's a polar cap. That's what we're doing. We need to parameterize that first. Well, parameterizing it is easy. Look at the surface we're dealing with. It's part of a sphere, isn't it? What's the radius of our sphere? Let's put all the electronics away so that we can pay attention to this.
It's minus 4 minus.
So ignore the part that we're looking at. Of the sphere, what's the radius of our sphere? Just 2. So it'll be 2 cosine theta sine phi, 2 sine theta sine phi, 2 cosine phi. So that's the parameterization of the whole sphere, right? It's the parameterization we use for a sphere. What dictates the portion that we're using is the domain. Well, if you just look on the xy plane, because that's how theta is determined, right? Xy plane. It's the whole circle, right? Theta goes 0 to 2 pi. Phi, on the other hand, measures declination. Declination, right? So start at 0, but it declines only to where the sphere intersects the cone. So it's right about there. Form that line. Phi is the angle that that line makes with the positive z-axis. You have to figure out what it is. It's actually not that hard to figure out. Where they intersect, they have to be true simultaneously, right? Well, that means x squared plus y squared is z squared, isn't it? Z squared would have to be 2, right? But what's z in spherical? Oh, it's this here, right? 2 cosine phi. Cosine squared phi is a half. What's that? A cosine. Cosine squared is a half. What's cosine?
It's just. No, wait, no.
Oh, 1 over square root of 2.
Which is root 2 over 2. Cosine of what angle is root 2 over 2? Pi over 4. That's what phi goes to. 0 pi over 4. Oh, why is it positive root 2 over 2 and not negative root 2 over 2?
Because of the patterns of the.
It's above the, it's above that. Oh, because it's a square root.
Square root gives you plus or minus. What's the total range for phi?
It's from 0 to. It starts at 0, so then
Right, and it goes to what?
In this case, 5 or 4.
Ignoring this, just total range for phi.
Just 0.
0 pi. Isn't cosine always positive? 0 pi? That's why it's the positive root instead of the negative. Because we're dealing with phi. There is your domain. I'll write the norm of the normal vector here. For a sphere, radius squared times sine phi, 4 sine phi. Well, it's xy, right? Yeah. No, it's yz. And so this becomes an integral over our domain, over our region D. We have to evaluate yz along the surface. Right? Y becomes 2 sine theta sine phi. Z becomes 2 cosine of phi. That's going to be what? 4 sine theta sine phi cosine phi, right? Times 4 sine phi dA. Yeah? We're going to have 16 integral 0 to pi, integral 0 to pi over 4. What? Sine theta, sine squared phi, cosine phi, d phi d theta, right? In 5 seconds, tell me what that integral equals.
16.
No,
It's 0.
What?
Why?
because of the grounds.
Which bounds?
Oh, because the zero bound is being.
The,
Oh, we know, just.
I think it's the theta,
Yes.
because sine
What's the period of sine?
is 0 to 2 pi.
It's just 2 pi. So the integral from 0 to 2 pi of sine is 0.
So,
You're left with 0 times an integral, which is 0. That whole thing is 0. Save yourself some time, right, and recognize that.
so I pay attention.
As I said.
I pay attention to it.
As I said, that took you 5 seconds if you recognize that.
It also helps that I've seen periods of that.
So I'm going to skip ahead. For the sake of time, there is definitely one problem I wanted to do. And that's this one. Evaluate flux. So the flux, and if it doesn't mention orientation, default is outward. So we're calculating the outward flux of this vector field, 4xz, negative y squared, and yz, through or across the unit cube. Flux is, in a sense, a flow. It's a net flow of a field. Outward flux would be the net outward flow through a surface. Unit cube. Cube where all sides are 1. And that point is the origin. Right, so if you imagine it, that is the positive z, positive x, positive y. Right, so it's the cube where sides are all 1 that's coming out at you. the way, this is a closed surface, right? So you may also see the integral represented this way. Much like with the line where if you have that circle, it represents that the curve itself is closed. That represents that the surface is closed. We did a closed surface, right? Or closed path circulation.
Yeah.
I'm not mistaken, we did actually a square, didn't we? Yeah, it was. How many paths was that? Remember, we broke it down into 4 paths.
Yeah. So this is
How many facings does a cube have?
6.
Which means our closed surface
So you're gonna
is the union of 6 surfaces that we have to evaluate.
So it's 6 individuals.
What?
That's why I wanted to do this.
So instead of taking all 6, wouldn't it just be changes in sign?
Not necessarily.
Well, I mean, you know that the cube has to have each surface needs to be equal because it's a cube.
That's true. The surface areas have to be equal.
Yeah.
But the flow through each of the facings don't have to be equal. It depends on how the vector field curls and everything.
Oh, right. Right.
Yeah, we're not doing surface area. We're doing flux. There is a much easier way of doing this. It's called divergence theorem,
That's not
but we haven't learned it yet. So I want to do this example to make the divergence theorem. You appreciate it way more.
That's. Was that talked about in different cube?
Divergence theorem is purely vector analysis.
I feel like
If it's discussed at all, it would be discussed in E&M.
that might be where I heard it.
Intro E&M
Yeah.
uses it. Because when you start to do like charge on a sphere, those are double integrals.
Oh, yeah.
But you also have to calculate flux, electric flux. That's probably where you've seen divergence theorem.
I don't really remember it, but.
So we're going to call the facings very simple, right? Top, bottom, left, right, front, back. Start with the front facing. Right, in physics, that represents an outward, circle dot, it's actually trying to make it. Circle dot represents an outward pointing vector. And a circle cross represents inward pointing, so I'm going to use that notation. So front, right, you're coming out. If you look at it, that's this facing here, right? So this is strictly a YZ plane, isn't it? X is always 1, isn't it? What does Y go from for the front? Remember, Y is the horizontal.
What? Or no? Just what?
0 to 4?
Not 4. I don't know where you got 4 from.
Oh, that's a Y. Is that 1 Y and 0?
Yes, that's the parameterization. Now I need the domain. So on the front facing, what does y go from?
It starts at the origin.
Well, it doesn't start at the origin.
Oh, well, 0.
It starts at the origin of the yz plane, I would agree. So it starts at 0 and goes to what?
It goes to
1.
1. What does z do?
It goes up 1.
3.
Starts at what?
0.
Starts at 0 and goes to 1.
Both y and z go 0 to 1. So I'm going to write it this way. That's very common mathematical notation. Right, that just means that y is 0 to 1 and z is 0 to 1. We need a normal vector. And it's outward pointing. Well, what's perpendicular? What direction would be perpendicular to the yz plane? It's the x direction, isn't it?
Yeah.
And you want outward pointing. So is that the positive direction or the negative direction?
Yeah.
Our normal vector just be I hat. Now for the back facing. Well, again, the back facing is a YZ plane, right? What's X in the back?
Is just
No.
which piece?
The back.
Oh, okay.
So what's X in the back?
Zero.
0. Y still goes 0 to 1, right? Z still goes 0 to 1? What is the normal vector going to be?
J.
You're still going to be perpendicular to the to a YZ plane, right? Which is still going to be the x direction. It's negative I hat this time, right? Because it's outward pointing, it has to go towards the negative direction. By the way, this looks hideous. This is actually a really, really nice vector field and surface to work with. Let's do the right facing next. Well, if you look at the right facing, isn't that an XZ plane? What's Y?
1.
What does X go from?
X is still 0. X is 0.
What's Z?
Also 0.
And what is the normal vector?
One X. No, it's J.
The left facing. What's Y?
0.
Does the domain change?
No.
And what is our normal vector?
negative J.
The top. Well now, isn't that an XY plane? Right? What's Z?
1.
What does X go from?
X is 0.
To what?
Zero to 0.
What's Y?
Also, yeah. So just
And what is N?
K.
Bottom. It's again an XY plane, right? What's Z?
0.
Is there any change in the domain?
No.
And what is N?
Negative K.
There are 6 surfaces. It's going to be the sum of the 6 flux integrals. Start at the top. Both Y and Z go 0 to 1. We want to evaluate our field for xz negative y squared yz along the surface G. X becomes 1, y and z stay the same, right? Dotted with n dA, which will be dz dy for us. X becomes 0 now, right? Now we're doing left and right, right? Which is dz dx, both are still 0 to 1. Y is 1, x and z stays the same. Now y is 0. It's now dy dx. Z is 1, X and Y stay the same. Finally, Z becomes 0. Like so. This is what we have to evaluate. Do the dot product. What do you get? What happens if you dot if you take a vector and dot it with just I? You have dot products work. What's I?
It's the,
What is it in component form?
um,
It's 1, 0, 0.
okay. Oh, right, because object from symmetry.
Isn't that first dot product just 4Z?
Yeah.
What's that second dot product?
it's
Negative.
Well, that's what negative I hat is, negative 1, 0, 0. What's the dot product?
which one?
The second one.
Oh, sorry, I was in, it's just 0.
What's that third one?
Is, yeah, negative 1.
What's that fourth one?
0.
What's that fifth one?
1.
What's that sixth one?
zero.
That's why I said this one was really nice. For z, well, first off, there's no y. Integral from 0 to 1 of dy is just 1. Integral of 4z from 0 to 1 is 2. That integral is really nice. That's minus 1. This integral, again, there's no x, so 0 to 1 of dx is just 1. Integral 0 to 1 of y is 1/2. We get a net outward flux of 3/2. So, key here is being able to parameterize a surface. So I recommend you read through the text. So it does give you several surfaces that are parameterized, as well as their normal vectors. Questions? I'd recommend trying to look through these. Look through the ones we didn't do and try them. You could even take a picture and plug into ChatGPT and see what ChatGPT says, right? Or maybe Math GPT. That might be a better option.
That's a thing.
Yeah. Math GPT is an actual thing.
That's,
The only reason I don't use it is because it can only solve problems from what I've read. It can't actually create math problems. You have to give it a math problem for it to solve.
Like you can't give it like a problem that you want, like a specific.
You can't ask it to write a problem, though. They won't do it. From what I've read, I've never actually used it, but I've looked at it, and it looks like it can only solve problems. Or give graphs, things like that.
that's interesting.
All right, so get into your group. Once again, down a number. Green's theorem. Green's theorem allows us to calculate the circulation of a vector field if it's two-dimensional as a double integral over the boundary of the closed curve. So it makes calculating circulation easier. Okay, let's just highlight that. That is Greek's theorem. It's just so nice.
And it's the Newton's counterclockwise.
Yes. But if you want to go with a negative orientation, there is a slight change made, so that's why I'm negative.
So you could use it for.
You could theoretically use it, but it's not going to be this point.
And then just multiply that.
First problem we're going to do is a verification, meaning we're going to calculate both the circulation directly and then using Green's theorem and show that they are identical.
Directly using what we can.
The directly as in the line integral. C, so the curve is the boundary of the region bounded by y equals x and y equals x squared. This isn't going to require me to actually plot this using Wolfram. Right, that's y equals x, right? And then that'd be y equals x squared. We're assuming counterclockwise.
So if you don't know that it's clockwise or counterclockwise, you just pick.
Because it's verified, I'm assuming counterclockwise. It will be stated explicitly for the exam. Yeah, on the side, there's not going to be another quiz. There won't be another quiz. I just don't have time to write it right now.
That was last quiz.
Yeah, I don't have the time to write another quiz. So I'm just going to say I have 5 quizzes, that's good enough. Right. So we're going to call this region D, right? Then our curve is the boundary of D. But if you notice, isn't the boundary of D 2 separate curves? So what I'm going to do is I'm going to say that bottom curve is curve 1, that top curve is curve 2. Then we can write this. I'm also going to explicitly write the vector field, because if you notice, it's currently written, the integral is currently written in differential form, which should bring nightmares to you. DQ.
DQ hasn't been terrible.
But that should look like the form that we use for exact, right? Yeah. Oh, now the whole conservative thing is making sense.
It's like you come into this. Crazy.
So I'm just explicitly stating that is the vector field that we're using. We do need this point of intersection now. What's that point?
So we'll find out.
Well, that's easy to do. What's that point? When does x equal x squared? There's only 2 points at which that's true. One of them's given to you.
Well, one.
One's the other one. The origin and 1. First, we're going to directly evaluate the line integral. Means we need two parameterizations, right? We need the parameterization for the first curve and for the second curve. First curve, well actually, yeah, let's do the first curve. First curve, C1. Isn't that y equals x squared? So why not just do t squared? T goes from 0 to 1, right? We're also going to need r prime. Right, r prime 1, or r1 prime. Which is what?
Which is 1 is 2.
R2.
It's just T. Or
What's the problem with that?
is that you're using T for both X and
No,
Y.
that's not an issue. What's your domain?
C1, C2.
Remember domains for T. Look at the orientation.
0, 0, 9.
That gives you the opposite direction.
Or could we just -1?
Could, but that might be an issue, like it was when we did the other one. That caused an issue. It should work, but I'm just going to be safe and do it the way I want to do it.
Yeah, I don't know what I was getting lured into trying to get into them. Okay.
So I use the 1 minus T.
Yeah, for the
Because x has to go from 1 to 0.
I remember something about that.
R2 prime is just -1, -1 then, right? So then our circulation integral from 0 to 1. F evaluated at R. But what was F? xy plus y squared and x squared. Right, so T times T squared is T cubed plus T squared squared. And then it's just cute. X squared, right? So T squared. Dotted with R1 prime dt. Plus integral from 0 to 1, f evaluated along R2 x times y, x times y, right? Plus y squared. And then it was x squared, wasn't it? Dotted with R2 prime dt. Integral 0 to 1, t cubed plus t to the fourth plus 2t cubed. Right, so now we're just doing the dot product. Plus integral 0 to 1, evaluate that dot product. This is going to become a minus sorry, there should be a 3 in there. Now it's just a matter of valuing those two integrals. T to the fifth over 5 from 0 to 1. 1/5. 3/4 t to the fourth from 0 to 1 is just 3/4, right? Then it's going to be minus. That's going to be what? Negative 3/4. 1 minus t to the fourth power. This becomes a plus. And then 1 minus 1 is 0. 1 minus 0 is 1, so that should still be a minus. Right, minus 3/4 in the end. Times negative 1. No, that's not right. Oh, that should not be a cube, that's why I wrote it down wrong. That should be a squared. That just becomes negative 1 minus t cubed, right? Now if I write that from 0 to 1, you get 1. So minus 1. Negative 1/20. That's what that comes out to. Put a box around that, and I'll label that number 1. Now we're going to evaluate the double integral. 3 things we need. First, let's describe the region. Oh, that's easy. X goes 0 to 1, y goes x squared to x, right? Now we need partial p partial y, and partial q partial x. There's p, there's q. What is partial p partial y?
Taking with respect to,
Partial p partial y.
oh, y. Is just gonna be x plus 2y.
What is partial q partial x?
2x.
Two x minus x minus 2y. That's the double integral we need to evaluate. First one, x. That's just going to be xy, right? But now that gets evaluated from x squared to x. X squared minus x cubed. Right? Because it'll be x times x minus x squared. Minus y squared. From x to x squared, that's going to be what? Minus x squared minus x to the fourth? Yeah. Just simplifies to the integral 0 1 x to the fourth minus x cubed.
Why is the 2y between x squared minus
What's the antiderivative of 2y
just 2y x squared?
with respect to y?
Oh, never mind. I didn't know I could take an extra to my bad.
Right, so now you're back on track. Right? So that's going to be what, a fifth minus a fourth? That integral?
Yes.
Gee, I'll make it 120. Look at 2. What's that value?
Same thing.
Green's name has been verified. As desired. So what did that one problem do?
A lot of radar.
Let's see. It required us to parameterize a curve, which in turn required us to find domains of vector value functions, take derivatives of vector value functions, dot products, and integrals. As well as describing a region, taking partials, and doing a double integral.
So what?
The beautiful thing about this topic that we're covering now, vector analysis, is it takes all of Calc 1, Calc 2, and Calc 3, and it puts it all together. It marries everything nicely. So the whole point of the calculus sequence, by the way, is these three theorems. Green's theorem plus the remaining two things that we'll be doing next week. That is the whole purpose of the calculus sequence.
Just to get to this.
Just to get to Green's theorem, Stokes' theorem, and divergence theorem.
So I took 3 calc classes to get to this.
It's the whole purpose of calculus.
I hate that.
Right? Like Calc 1 built up to the fundamental theorem of calculus. Calc 2 had no purpose.
Did you say calc 2? I didn't know.
It really doesn't build up to anything, does it?
No, I've used none of calc
Yeah.
2 in this class, which is great.
And Calc 3 builds up to the three theorems. But the whole purpose of the entire calculus sequence is to get up to these three theorems: Green's theorem, Stokes' theorem, divergence theorem. Because those three theorems are going to allow us to evaluate anything. Oh, by the way, I haven't shown it, so remind me next week, and I'll show you the integral forms of Maxwell's equations. Because I showed you the differential forms already. I'll show you the integral forms later. That required line integrals and surface integrals.
Oh, speaking of differential, you told me to remind you about.
I have a message. Yeah, it's flagged. So I'll just forget to do it and blame you anyway.
Wow. This video is still recording.
Yeah, but I can edit it.
Dang. My phone's still recording.
You do not have my permission to record this course. It's copyrighted material.
Dang. It was just recording the last 5 minutes.
It's still copyrighted material.
Dang. It's not getting published anywhere, so copyright laws don't claim.
Actually, yes, it does.
If you're not using it, if you're not publishing it,
Copyright is very broad.
depends on your country.
Copyright is very broad. Don't forget the homework.
I don't know. So is the homework in the final, the last 2 things?
Homework 13 and
Damn. Maybe it's the end. I think this will end up being the highest, unless I like really beef for the final, which I don't think I'm going to.